If you haven't done so yet, please pause the video and try to solve the question on your own before listening on. We're going to go ahead and draw a picture of the scenario that's being described. On the left-hand side, we have the particle, the unstable nucleus, as it's being called in the question, initially at rest at the origin of a coordinate system. It then spontaneously decides to explode and fragment into three pieces. We've got one piece moving upward along the positive y direction, a second piece moving to the right along the positive x direction, and then a third piece whose velocity and mass we don't currently know. And in fact, our first step in the question is actually to find the mass of the third particle. Now, it should make sense that the original mass, which we could call m, has to equal the masses of the three particles after this explosion or this fragmentation. So we can fill in the known value for the original mass, which was given to us in the question, and then also m1 and m2 in order to find m3. So there we've plugged in all the known masses. You would have to add the two masses and then subtract them over to the right-hand side. And you should be able to determine a value for m3 of 3.6 times 10 to the minus 27th kilograms. So that's the mass of the third particle. We could fill that into the picture. Okay, now because this is essentially a collision problem, we're going to be able to conserve momentum. If you think about it, it's actually a reverse collision, where you have a particle that's initially at rest, and then it explodes into three pieces that are kind of flying every which way. So it's a collision that's basically being run in reverse, but it is a collision nonetheless. And we know that in collisions, we can conserve momentum. Now, in this case, we're going to have to conserve momentum in both the y direction and in the x direction. Let's take a look at the y direction first. So here we have the conservation of momentum equation for the y direction. On the right-hand side, we have the initial momentum, and we noted earlier that initially the particle was at rest, so that means the initial momentum would be 0. On the left-hand side, we have the sum of the momenta of the three different particles, m1, m2, and m3. Don't forget that momentum is mass times velocity. Now, what we can do is solve this equation for the velocity of particle 3. So we're going to have to subtract the m1 v1 to the right as well as the m2 v2 and then divide by m3. So there we have isolated the velocity of particle 3 for the y direction. Before we just haphazardly plug into the right-hand side to solve for that velocity of particle 3, we want to be careful about the velocity for particle 2. Remember, we are conserving momentum in the y direction right now. If we look at the picture, we can see that particle 2 is not moving in the y direction, so its velocity in the y direction will actually be 0. Particle 1, on the other hand, is certainly moving in the y direction since it's traveling up the y-axis, so we will be plugging in 6 times 10 to the 6th for the v1. But again, v2, the velocity of particle 2, has to be 0 for this equation because we're looking at the y direction velocity, and that particle is moving only in the x direction. So with that in mind, we can go ahead and plug in the known values. And when you compute that, you should get roughly negative 8.33 times 10 to the positive 6th meters per second. Notice that the negative sign indicates that particle 3 is moving downward in the y direction. We'll say more about that in a moment. This is going to be, again, the velocity of particle 3 in the y direction, but we also have to find the velocity in the x direction. So we're going to go through the conservation of momentum again, but this time we'll be doing this in the x direction. So here is the conservation of momentum in the x direction. Notice we're using x subscripts for all the values. We have the three particles on the left-hand side for the final momenta. The initial momentum, once again, is equal to 0 because the original particle was at rest. We want to solve this equation for the velocity of particle 3 in the x direction. So we're going to have to subtract this term to the right-hand side, and then divide both sides by m3. Now for velocity 1 in the x direction, we want to look at particle 1, which again is moving along the y-axis. And since particle 1 is moving along the y-axis, its velocity in the x direction will be 0. So don't forget that v1x is going to be 0. With that in mind, we can plug in all the other known values. And when we compute this, we get approximately negative 9.33 times 10 to the 6th meters per second. The fact that it's negative indicates that the final velocity of particle 3 is actually moving to the left. So now we have to take the velocity in the x direction and also the velocity in the y direction that we found earlier and then combine them to get the overall final velocity. And to do that, it's going to be helpful to draw a picture of the x velocity as well as the y velocity. So here we've set up a y and x axes, and again, since the velocity in the x direction is negative, what we can do is project a vector pointing to the left. Try that again. We can project a vector pointing to the left along the x-axis. We're pointing it to the left because that velocity was negative. And so this would be our velocity 3x. And then the velocity in the y direction of particle 3 also is negative, so we can project a vector pointing straight down, parallel to the y-axis. That's the velocity of particle 3 in the y direction. The overall velocity would be the hypotenuse of this right triangle that we're drawing. That's what we're looking for. And of course, to find this resultant velocity, which we can just call v3, we can use the Pythagorean theorem. So we would have c squared, or in this case v3 squared, since it's the hypotenuse, is equal to the v3x squared plus the v3y squared. And then to solve this for v3, we just take the square root of both sides of the equation. And now that we've isolated v3, we can plug in the values that we found earlier for v3x and v3y. And when we plug that into our calculators, we should get approximately 1.3 times 10 to the power of 7 meters per second. So this would be the correct answer for the magnitude of particle 3's final velocity. What we also are asked to find is the direction, which is this angle right here. Now we can see that opposite to this angle is v3y, adjacent to the angle is v3x, and since we have opposite and adjacent, we could use tangent, because we know the tangent of an angle is equal to the opposite over the adjacent. Therefore, the angle will be the inverse tangent of opposite over adjacent. Again, the opposite is v3y, and the adjacent is v3x. So let's plug those in. And then we can see that the angle turns out to be roughly 41.8 degrees. If the question is asking you to measure that angle from the positive x-axis, which would be this line right here, notice that you would have to measure all the way until you hit that red v3 vector right here. We just said that this angle is 41.8 degrees. We would have to add 41.8 degrees to 180, right? Because we know from here to there is 180, and we need to go that extra angular distance of theta. So we need to add 180 degrees onto our answer, and when we do that, we get roughly 222 degrees from the positive x-axis. And so this would be the correct answer for the direction. Thanks for watching. If you liked the video, click the thumbs up icon and also subscribe to the channel. Remember, you can send in your own question to the email address on the screen, and I'll do my best to answer it on YouTube.